Hey everyone, welcome to our senior design presentation. We are team 2 of the CPU overclocking project, and today we're presenting the external performance unit, which is a modular cooling upgrade kit. So we're a group of 4 mechanical engineering seniors. Myself, Dawson in the bottom left here, led more of the systems integration and controls. Van in the top left here focused on the electrical systems and data acquisition. David in the top right owned mechanical design and CAD. And then Joel in the bottom right here led the CFD and experimental testing. And our faculty advisor is Dr. Darshan.
As CPUs have become more powerful, thermal management is the single biggest obstacle to performance. When a CPU gets too hot, it protectively slows itself down, a process called thermal throttling. Mid-range coolers top out at about 265 watts. If users need more, they could end up getting rid of their existing cooler and spend over $250 on a premium replacement. This isn't an affordable middle ground, so we set out to fill that gap. So we chose this topic because the demand for high-performance computing is exploding. AI usage, simulation, rendering, and gaming all generate extreme heat loads. At the same time, the industry encourages a wasteful cycle of replacing functional hardware. So we wanted to prove there's a smarter, more sustainable way to get higher performance. So we defined 4 critical performance targets. First, increase thermal dissipation capacity to 320 watts, about a 20% improvement. Second, keep noise under 35 decibels while quieter than the stock cooler at the same 265 watt base load. Third, keep the entire modification kit under $65. And fourth, make installation possible in under 20 minutes with just simple tools. So before committing to a design, we conducted technology research. On the cooling side, we evaluate everything from thermal interface materials to exotic options like vapor compression refrigeration. And on the control side, we compared microcontrollers versus single board computers, fuzzy logic, and more. But we narrowed it down to 3 finalist concepts. And the flaws we ran into included with the hybrid internal mod, which risked colliding with the motherboard components, and the chain radiator loop exceeded our budget at over $175. Whereas the external performance unit, or EPU for short, provided the best balance of thermal performance, acoustics, cost, and compatibility. So the EPU works by adding a second row of fans on the exterior of the PC case, creating a push-pull configuration through the radiator. This effectively doubles the system's static pressure capability, allowing air to overcome the high aerodynamic impedance of the 38mm thick radiator core. Modeling predicted about a 31.3% increase in volumetric airflow, which lifted the thermal ceiling to nearly 348 watts. And sharing the pressure work between 2 fan rows also lets us run each stage at lower RPM for a given cooling job, which is a big part of how we were going to improve the acoustics.
The EPU housing is 3D printed from PETG, chosen for its high temperature resistance and dimensional stability. It houses 3 Arctic P12 Pro 120mm fans, which are optimized for high static pressure. The housing mounts on the PC case using standard number 6-32 machine screws. A magnetic lid provides toolless access for maintenance and dust filter replacement. The entire assembly fits within the same footprint as the original cooler. Here you can see a complete CAD assembly on the left, the full system integration with the EPU mounted on top of the Li LandCool 207 case. In the center, the isolated housing base, showing the PETG frame and internal rib structure. On the right, the baseline Arctic Liquid Freezer 3 cooler that the EPU is designed to enhance. On the left is our SATA direct drive reference schematic, 5V and 12V from SATA fused 12V bus, Arduino PWM to all fans, leader tack on D2. On the right, the bullets walk through topology, firmware, and acoustics, and below is the real assembly in the housing. Firmware generates 25 kHz PWM and watches the tack line for stalls. For sound, we use push-pull and lower PWM where thermal is allowed, matching the acoustic data we show later. To validate our design analytically, we performed computational fluid dynamic simulations using ANSYS Fluent. We modeled a representative section of the radiator with accurate fin density and pipe dimensions. After refining the geometry in ANSYS Discovery and defining fluid regions, we generated a high-quality volume mesh in ANSYS Mechanical. The simulations ran 4 scenarios comparing single fan versus push-pull configuration at both low and high RPM. The CFD results confirmed our analytical predictions. At maximum RPM, the push-pull configuration increased the heat rejection rate by 4.5% and the airside heat transfer coefficient by 14.5%. but the most significant advantage is acoustic. By sharing the pressure load between two fan rows, we can achieve the same cooling at 30% lower RPM, which translates directly to a 9.4% noise reduction. On the left, we have the PC used for testing with the EPU installed on top. On the right, we have our telemetry UI alongside Ryzen Master and Task Manager to confirm CPU load and temperatures.
Our testing methodology followed industry standard practices. We used Prime 95 to generate consistent worst-case thermal load. HWI NF064 logged all telemetry data. Each test ran for 45 continuous minutes to ensure the system was at thermal equilibrium. Acoustic measurements used a calibrated SPL meter at 1 meter distance. All thermal results are reported as delta T to eliminate ambient temperature as a variable. The thermal results exceeded every target. The system maintained a continuous 336.3 watt heat load, well above our 320 watt goal. The CPU temperature plateaued at 82.6 degrees Celsius, which is 17 degrees below the throttling limit. This flat plateau confirms that true thermal equilibrium was achieved. The calculated coefficient of performance was 25.1, showing exceptional cooling efficiency for the electrical power consumed. The power consumption peaked at just 13.39 watts, well below the 20 watt safety limit of the system. We also validated the firmware's stall detection failsafe. During testing, we introduced simulated stall faults at the 9-minute and 26-minute marks. The acoustic results were one of our proudest achievements. The stock cooler produced 38.1 decibels at 265 watts. With the EPU engaged at the same load, we measured 29.3 decibels. Even at a higher CPU load, we stayed near our design noise budget. Here's a complete results summary. Every single critical performance parameter was met or exceeded. We achieved 336.3 watts thermal capacity, a coefficient of performance of 25.1, 31.5 decibels at maximum load, a power draw of just 13.39 watts, exhaust delta T of only 3.16 degrees, instant stall detection, and a total bill of materials cost of $64.05.
We actively incorporated advisor and peer feedback to redefine the EPU. We adjusted CFD boundary conditions with exponential scaling for highly accurate temperature predictions. For validation, we extended our thermal stress test to 45 minutes to ensure true equilibrium. Finally, our FMEA of over 50 failure modes drove critical safety additions, including an inline fuse and a firmware-based stall detection failsafe. The EPU offers significant broader impacts. Economically, delivering enthusiast-grade performance for just $65 provides high-performance computing to budget-conscious users, saving them over $185 compared to premium replacements. Environmentally, our upcycling approach keeps functional radiators and pumps out of landfills. Furthermore, localized 3D printing with high-temperature PETG allows for low-cost, accessible manufacturing without complex global supply chains. Our prototype proved mid-range hardware can achieve enthusiast-grade performance at a quarter of the cost. The EPU exceeded expectations, dissipating 336 watts without thermal throttling and maintaining a quiet 31.5 decibels. Passing all 7 of our rigorous performance metrics validates the physical viability of our upcycling philosophy. Push the EPU towards commercialization, future work will focus on 3 key areas. First, implementing a firmware RPM sync offset to eliminate subtle harmonic beat frequencies. Second, conducting accelerated live testing to formally certify a 25,000-hour mean time between failures. Finally, scaling manufacturing from 3D printing to injection molding. Thank you for watching our presentation. We are proud of what our team accomplished this year.